Good day. In today's lesson, or in this video particularly, we'll be looking at an analytical geometry. More specifically, we'll be revising last year's geometry, as I feel this is the most essential part of geometry. So we're going to be focusing mostly on grade 11 geometry. So quickly going to go through a few things that you have to remember, and then I'm going to try to give you a few tips and tricks on how to do geometry. Now, before we start even thinking about analytical geometry, or not analytical geometry, sorry, Euclidean geometry, um, before we even start looking at Euclidean geometry, there's a few things that we have to know and remember. We have to remember what congruency is. Now, congruency is when two shapes are exactly the same. Now, with Euclidean geometry, we'll be mostly focusing on triangles. Now, triangles are congruent when the following is true. When either all the sides are equal, or when at least two sides where the angle are the same. Then there's also a situation where we can have two angles and another side. And then lastly, there's one specially for right angle triangles, which is um, perpendicular angle, hypotenuse, and side. Okay, so this is especially for that. Now, this is especially useful when we start to prove Euclidean geometry, and then in test you can use this as well as a handy tool. Then similarity is occurs when shapes are in relationship to each other, or what I mean by that is one shape is exactly twice as big as the other one. So when shapes are in relationship to each other. In regards to their size. Now, mostly this occurs when all angles are the same, or when corresponding sides are in relationship to each other, meaning um, um, now normally when they write this in a something, you'll see that it's something like, let's just give the computer a while to catch up. I think I might have just confused it a bit. So normally they normally write it as AB divided by CD equals to um, a um, D divide, no, not D. Let me just change that, otherwise I'm going to confuse myself. E equals to BC divided by EF equals to AC divided by DF. Normally, when those sides that are corresponding, they form a relationship with each other. Now, all these lead us to the grade 11 theorems, because the grade 12 theorems you learn are just basically proving similarity at the end of the day. So, if we have a look, the first theorem we had is a line drawn from the center of a circle perpendicular to a chord bisects that chord. Basically, what that means, if you had your circle, you'll have a line, and if you take, or if you have your chord, and if you take a line and you draw it from the radius and it's perpendicular to that chord, it bisects that chord. Now the converse is this is also true. So if you have a chord or a line drawn from the center of a circle that bisects a chord, then that line is perpendicular to that chord. Next one, we will not be focusing on proofs as a side note, because I did upload a little book that shows you the proofs. The next theorem we have is if the perpendicular bisector of a chord is drawn, it passes through the center of a circle. So what that means, if we have a circle and we draw a chord, and we take the perpendicular bisector of that chord, then that will always cut through the midpoint of your circle. Now, you can use this to establish the midpoint of the circle by making use of a situation where you can have, you can draw a few chords in, and then you can try to draw the perpendicular bisectors. And there where they overlap, that will be the midpoint of your circle. Okay. Next theorem is the angle subtended by an arc at the center of the circle is double the size of the angle subtended by the same arc at the circle. So that means if you have your circle and you have an angle at the midpoint and that's subtended by an arc, then say there is another angle which is on the circle, which is also subtended by this arc, then this angle over here, it's twice the angle at the circle. Now there's a few ones of these. There's one that looks something like, similar to this, in which case this would be your angle at the circle, and this would be your circle or angle that's twice the size of this one. And then there's also a weird one that looks like this, which is basically this, just the first one taken and manipulated a bit. Okay. The next one, it's the bow tie theorem, which we all know well by now. Now, it states if angles on a circle are subtended by the same chord or arc, then the two angles are equal. Meaning, if we have a circle, whoopsie daisy, if you have your circle and then you have your angles that are subtended in the same segment, meaning they fall in the same area or same segment, then those angles are equal, which is your bow tie, essentially. Then theorem 5, if a quadrilateral is cyclic, then the opposite angles are supplementary. Now this one uses all the previous theorems to prove, but basically what it says, if you have your cyclic quadrilateral, then opposite angles together are 180 degrees, or is 180 degrees together. The next one comes down to tangents to a circle. Now there's an unmentioned one here. It's where you have your circle. If you have a tangent to the circle and there's a radius drawn to the point of contact, then that will be perpendicular. Now this one goes unmentioned in this video until now. Then we use this theorem that I've just talked about, the one about the tangent and the radius. We can use that to prove these tan-chord theorems. Now, the first tangent to the circle theorem is if two tangents are drawn from the same point outside a circle, then they are equal in length. So that means if you have your circle and you have a point, say P over here, and both of your tangents go through this point P, then the point between the circle and the point will be equal in size. Next theorem, it's the tan-chord theorem. Now this one states that the angle between a tangent and a chord drawn from the point of contact is equal to the angle in the alternate segment. So that means you have your circle. Ooh, that's a horrible looking circle. If you have your circle and you have your tangent over here and you have a chord drawn from this point of contact toward another point, then this angle over here, it's equal to the angle over here. This angle in the alternate segment. So that's basically it. Now these are your grade 11 theorems, and I don't go through the grade 12 theorems because I feel the grade 11 theorems are more important. Not necessarily more important, but they build up to the grade 11 theorems. So this was just a quick breathe through of that. Now to give you a few hints. With any geometry, expect to think out of the box. Think out of the box. The reason for this is most of the times they'll combine these theorems in ways you couldn't or can only imagine. So the question is never going to look exactly the same as the ones you did in class, no matter how hard you try. So here you're going to have to think out of the box. Another thing is when they give you a question in which you'd have to use two triangles. So triangle A, B, C, and triangle A, C, D also. Normally, in this notation, if you write this notation, or if they tell you prove that something is congruent, normally in this notation, they put it so that the corresponding angles are in the same position. That means A would be corresponding to A. B would be corresponding to C. And C would be corresponding to D. So A corresponds okay, this cannot be C, this has to be E. Now this is especially handily tricky sometimes if you're stuck because they can give you hints like this. Another thing is know your theorems. Know your theorems off by heart. Okay. This is especially important. If you don't know your theorems, you're going to struggle extremely. And then practice. Normally in math, I would not say practice yourself to death, but with geometry, the more you practice it, the easier it is going to be. Now I'm falling over my words. The easier it is to see the type of questions or to see the answers floating around. And with that, we've done a run through of Euclidean geometry.